Hi, and welcome to the first of 3 webinars in the Power Quality Measurement series. In the first series, we're going to start to understand harmonics and how to make measurements on distorted waveforms. The second in the series focuses on IEC harmonic compliance measurements, and the third is concentrating on the IEC flicker compliant measurements. My name is Bill Driver. I'm a product manager at Yokogawa, and I will be your presenter today. The focus today is going to be on harmonic analysis on distorted waveforms. We will cover what harmonics are, how they're generated, adverse effects of harmonics, how to measure them, and end with some measurement examples. Before we jump in, I want to give some background on Yokogawa. Yokogawa has over a 100-year history in power, where we were the first to make and sell electric meters in Japan. Yokogawa has expanded to 84 companies worldwide and are in 59 countries. The United States operation pictured here is based in Noonan, Georgia, where we host our services, support, and calibration teams using our A2LA and ISO 17025 accredited calibration lab. Harmonics are present in our electrical systems, and we will spend some time understanding what they are and where they come from. A good place to start is from our source of power, our utilities. All utility power is distributed as a sinusoidal voltage. Let's review how we get a sinusoidal shape. When electric current flows through a wire or conductor, a circular magnetic field is created around the wire where strength is related to the current value. When a single wire moves through a permanent magnet field, an EMF or electromagnetic field is induced. This creates an instantaneous voltage that depends on the rate or speed, which is indicated by omega, at which the coil is rotated depending on the angle of rotation, theta. Power generation in the world is generally 3-phase, but for the purposes on this discussion, we'll look at power in a single phase to illustrate harmonics. When we talk about a load in a circuit or power system, we're referring to the electrical component or portion of the circuit that consumes active power. When an electrical load is connected to a voltage source, it draws current to perform work. If the current follows in the same sinusoidal pattern as the voltage, then the load is said to linearly follow the voltage, and in short is called a linear load. When a sine wave voltage is applied to a load of linear elements, like a resistor, inductor, or capacitor, the current will always be a sine wave of the same frequency and wave shape, with varying phase. However, if the connected load does not follow the sinusoidal wave shape of the voltage, then the load is called a nonlinear load. Nonlinear loads cause stress on the transformers and generators that make up the power system, also known as the power grid. The stress has been found to be primarily thermal in nature. Power systems carrying nonlinear loads are less efficient, so it's important to find them and take corrective actions to reduce their negative impact on the power grid. In this example, nonlinear loads can be diodes, MOSFETs, BJTs, and similar components. Harmonics have only been around over the last few decades since the introduction of electric drives for motors, fans and pumps, and power supply switching circuits such as rectifiers shown here as part of the motor controller or AC drive. An AC motor drive has AC inputs that cuts and chops the input sine waves at the input, then converts the chopped AC waveform to DC, resulting in a waveform at the output that has much more signal content than the fundamental waveform that it started with. This cutting and chopping and filtering results in harmonics and distortion. Just how much distortion is caused by harmonics? Each linear device has its unique contribution to harmonics with predictable behavior at specific harmonic orders. Next, we want to look at the harmonic waveforms and define sequences as it relates to the order or multiple of the fundamental. Harmonics refer to all sine waves whose frequency is an integer multiple of the fundamental wave, normally a 50 Hz or 60 Hz sinusoidal power line signal, or between 0 and 2 kHz for rotating machines. Harmonics are a distortion of the normal electrical current waveforms generally transmitted by nonlinear loads. Unlike linear loads, where the current draw is proportional to and follows the waveform of the input voltage, nonlinear loads, like variable speed motors, draw current in short, abrupt pulses. When the fundamental wave and subsequent harmonic components are combined, waveforms become distorted and interference occurs. The red waveforms are the actual shapes of the waveform as seen by the load, due to the harmonic content being added to the fundamental frequency. In this illustration, the multiples of blue harmonic waveforms sum together, resulting in a distorted red waveform. Harmonics are generally classified by their name and frequency. For example, the second harmonic of the fundamental frequency at 50 Hz is 100 Hz. They are also given a value for sequence. Harmonic sequence refers to the phasor rotation of the harmonic voltages and currents with respect to the fundamental waveform in a balanced 3-phase 4-wire system. The sequence is based on the rotation of their magnetic field. Positive sequence harmonics create a magnetic field in the direction of the rotation. The fundamental frequency is considered a positive sequence harmonic. Negative sequence harmonics develop magnetic fields in the opposite rotation. This reduces torque and increases the current required to operate the load, which in turn uses more energy and is economically wasteful. Zero sequence harmonics do not produce a rotating magnetic field of any kind. Instead of canceling out, they sum together in a high neutral current, which in turn wastes energy and produces damaging overheating. The zero sequence harmonics are a set of special harmonics called triplens. Triplens are multiples of the third harmonic, so for example, third, ninth, 15th, etc., hence their name, and are therefore displaced by 0 degrees. Zero sequence harmonics circulate between the phase and neutral or ground. Unlike the positive and negative sequence harmonic currents that cancel each other out, third order or triplet harmonics do not cancel out. Instead, they add up arithmetically in the common neutral wire, which is subject to currents from all three phases. The result is that current amplitude in the neutral wire of these triplets could be up to 3 times the amplitude of the phase current at the fundamental frequency, causing it to become less efficient and overheat. We can measure the levels of triplet harmonics in our system by performing harmonic analysis on our system. But performing harmonics is not as straightforward as you think. We are familiar with the fast Fourier transform, but there's another method called the discrete Fourier transform. The discrete Fourier transform, or DFT, is a powerful tool in digital signal processing as it finds the spectrum of finite duration signals. It does this by converting a finite sequence of equally spaced samples of a function into the same length sequence of equally spaced samples. The FFT, or fast Fourier transform, is what the name applies, a faster method for evaluating a DFT. For example, with a sequence of 1024 samples, a DFT will process 1024 points squared, resulting in over 1 million points to process. An FFT computes the same results in n log steps, resulting in only 3,000 points, significantly reducing the time for computing. Fourier stated a complex waveform could be understood and mathematically defined as a composite of a fundamental frequency sine wave with other sine waves in multiples of that frequency. These waves are called harmonics. By applying the Fourier transform, we can break down the complex waveforms into its basic components, which happen to be sine waves at various frequencies, amplitudes, and phases, as shown here with the blue traces. The yellow trace is a result view of the analyzer performing a DFT or FFT, indicating a pulse at a specified point in the frequency domain pertaining to the multiple of the harmonic frequency. The amplitude of the yellow pulse indicates the energy at each harmonic. To better control harmonics and how they are defined, measured, and interpreted by different interest groups, the International Electrotechnical Commission, or IEC, formulates a series of standards as well as IEEE and other military standards. These standards include IEEE 519. This is from the Institute of Electrical and Electronics Engineers, also known as IEEE. And 519 is a system guideline for setting limits on voltage and current distortion. It is often referred to as IEEE 519 or IEEE 519-2014. IEC 61000-3-2 and IEC 61004-7 both define the limits for harmonic and current emissions, what we also call EMC. IEC 62301, what we call standby power. This objective is to provide a method to test and determine the power consumption of a range of appliances and equipment in standby mode. In the United States and North America, the Energy Star standard is typically used for testing these limits. Mill Standard 704, we use that to test Air Force aircraft systems. DO 160 tests commercial aircraft. Mill Standard 1399 tests Navy shipboard systems. And these standards are all useful to note since each standard will require compliance with specific standards. We will discuss IEC 61003-2 more closely in the examples following. An industry standard for measuring harmonics is to measure total harmonic distortion. Total harmonic distortion, or THD, is the ratio of harmonic content to the fundamental. THD is expressed as a percentage of the fundamental. The higher the percentage, the more distorted the waveform. The THD calculation has 2 definitions based on UL or IEC standards. The main difference is in the denominator, where UL calculates based on the total harmonics, while the IEC method calculates using the first harmonic. It's very important to know the method of calculation with your test equipment. Yokogawa power analyzers provide an option to select between these methods. IEEE 519 standard defines the acceptable levels of TDD, or total demand distortion, at a point where the customer ties into the power grid, which is called the PCC, or point of common coupling. TDD is a moving average of the THD based on the system rated current value. Note that the calculation for THD is instantaneous, and the calculation for TDD has a denominator of I sub L, where I sub L equals the sum of all currents corresponding to a maximum demand during each of the previous 12 months divided by 12. Another equation that's important to understand is frequency resolution. Frequency resolution is the distance in hertz between two adjacent data points in the DFT. The resolution of an FFT is defined as the sampling rate divided by the number of data points. The sample rate determines the bandwidth of the FFT, so as sampling rate increases, so does the bandwidth. The higher the sampling speed, the lower the FFT resolution. So let's look at an example with some numbers. If our sample rate is 10 megasamples per second and have a record length of 10 kilopoints, we divide 10 million samples divided by 10 kilopoints, and we get 1,000 hertz, or 1 kilohertz. So this means the smallest frequency change we can detect is 1 kilohertz. Also note that increasing the memory depth results in slower computation. It's important to remember that harmonics are a multiple of the fundamental. So if the fundamental is 50 hertz, the second harmonic will occur at 100 hertz. In terms of buckets or bins, 100 hertz is the second harmonic and fits into the second bin. Sometimes the math isn't exact to fall into the exact bin of interest. When this happens, the accuracy of the harmonic measurements are compromised because energy in a specific harmonic order is spread over two bins. This is called spectral leakage. The concept of spectral leakage is easier to understand when considering the windowing used in the calculation. In the top example, we look at how the FFT is calculated. The window of the data is created and processed by the instrument. Spectral leakage occurs when a non-integer number of periods of a signal is sent to the FFT. The spectral leakage lets a single tone be spread among several frequencies after the FFT operation. This makes it hard to find the actual frequency of the signal. Let's show this with an example signal at 400 hertz. The calculation for K, or bucket number, is 102.4, with a frequency resolution of 3.906 hertz. This means the width of the bin is 3.9 hertz, but the bin falls at 102.4, which is between two whole numbers. The result is the image at the left, which splits the energy between bin numbers 102 and 103. What is desired is the image at the right, which puts all the energy in a whole number bin, providing a more accurate representation of the actual harmonic energy in the system. Spectral leakage is not due to an FFT, but due to the finite observation time. This gives rise to two problems. The spectral component of the desired signal no longer contains the complete energy. Rather, it also contains the energy of the adjacent components and noise, thereby reducing the signal-to-noise ratio. And two, the spectral leakage from the larger signal component may significantly overshadow other smaller signals, making them difficult to identify or detect. This is due to an increased noise floor. These issues occur because of math, because the fundamental signal does not always divide well with the given memory and sample rate. Because the harmonic bins are integer multiples of the harmonic, when the bins of the equations we previously reviewed do not equal the bins of the true harmonic, the leakage will occur. Luckily, there's a solution to prevent spectral leakage, and that is with the use of a PLL to lock to the fundamental frequency. On the left, the method of an FFT without a PLL. Note the increased noise floor. On the right, the instrument uses a PLL to align the bins to the signal being measured. The PLL, or phase lock loop, is an effective tool to eliminate spectral leakage. For a PLL to work, it needs to have a clear distinction of pulse changes through a zero crossing. Typically, a zero cross detector will detect the frequency of the input circuit and pass the result to a PLL circuit. The PLL circuit is a control system designed for tracking the input frequency and generating frequencies at integer multiples of the input frequency. The output of the PLL circuit is then passed to the A to D, where the instrument then can perform an FFT analysis. When we say power analyzer is purpose-built, this is one of the things we mean. Special filters built in parallel with the A to D signal path. This is how we detect zero crossing. The PLL allows the instrument to make decisions based on the math. This table shows how sample rates are adjusted with the fundamental frequency. The two images are taken with the same signal acquired with and without a PLL. You can see the spectral leakage shown. To put actual numbers in this example, we use 100 Hz for the fundamental, and a harmonic of interest is 400 Hz. In the traditional FFT method, the math translates this to the 102.4th bin. Since it must be an integer, the energy spans 2 bins. In a synchronized instrument, the fundamental frequency of 400 Hz is multiplied by 1024. This value is from the table above, resulting in 102.4 kilohertz with a memory setting of 8192 points. This makes the math work for an integer number of 32 bins with a resolution of 12.5 Hz, providing an accurate representation of the energy at 400 Hz. We've been talking about harmonics theoretically, so I'll share some actual measurements taken on a laptop power supply. I performed an FFT analysis, displayed the harmonic orders, and I ran a compliance test on this power supply to IEC 61003-2. This generic block diagram shows we should have plenty harmonics present in the signal due to nonlinear devices in the AC-DC rectifier stage. Using a Yokogawa power scope, this is a PX8000, we captured the single phase of voltage and current. The voltage waveform is close to ideal, looking like a non-distorted sine wave. The current waveform has distortions due to nonlinear devices in the power supply. The nonlinearities will cause some harmonics, which we will be interested in measuring. The screen on the left is the FFT view showing 50 orders of the harmonic, which is 60 Hz. The cutoff is set to 3 kHz. The screen on the right is using the PLL method, so the spectral leakage is minimized, resulting in clear bins and a lower noise floor. The box on the right also shows the PLL indicating it is locked at 59.986 Hz. Now if we compare both of these for the values of the bins, the FFT on the left has a marker on the fundamental indicating 60 Hz. There's a Y1 value of negative 13.125 e to the 0 to indicate the current level. This makes it very difficult to calculate the current values at each peak. Now on the right, with the bins, we see the markers indicate a readout of 221.82 milliamps. Much easier. Using a different instrument from Yokogawa called a power analyzer, I'm displaying a table view that lists the sequential orders and current levels and percentages. You'll notice the prominence of the odd harmonics as opposed to the even harmonics. The even harmonics are contributing less than 0.5% to the overall system. You can also notice the Triplen Harmonics, 3, 5, and 9. They're higher than expected, or as expected. The ability to see the exact bin and its contribution to the system is very important when measuring to a standard, which may have specific requirements. Say, for example, you need to only measure up to the 50th order. You can specify that and look at all those harmonics that roll up to 50 to 1. We took the same power supply and performed IEC 61000-3-2 test. We classified it as a type A EMC radiation device, and luckily we passed. We get a test report that has our test data with timestamp and all pertinent information. And this specific test shows a table with up to 50 harmonic orders and compares it to the limits that are defined by the standard. The list of supported standards that Yokogawa supports are on the right, with 61003-2, 3-12, 4-7, and some of the Japanese standards, JIS. We know the equations, and now we can better understand spectral leakage. Let's look at the instruments that can perform these harmonic measurements, and let's talk about some of the trade-offs. There are many instruments on the market that can perform harmonics or FFTs, and each have their own advantage. We categorize these instruments as streaming or digital storage. It's an important distinction because each of these instruments calculates power, therefore harmonics, differently. In general terms, the trade-offs on the streaming instruments, they perform more accurately over time, where on the digital side, they are more flexible and have more functionality as far as added triggers and looking at waveforms. A power analyzer is the best device for accuracy, where an oscilloscope will lack accuracy but is the most flexible. One important consideration for harmonic analysis is accuracy. Most DAC or oscilloscope products don't list specifications for harmonics. Power analyzers give the same level of detail for voltage, current, and power harmonic accuracy readings. Is this good or bad? Well, it depends. If you want a general idea of harmonics present in your system, accuracy specs aren't required. If you're designing a product to comply with standards like IEEE 519 or IEC 61000 3-2, or you're threatened by the power company they're going to shut down your power because you're putting too much dirty power or harmonics back onto the grid, you might be willing to change your instrument for level of confidence in measuring your device. Yokogawa power analyzers and power scopes provide guaranteed accuracy for power, voltage, current, and harmonics at the full bandwidth of the instrument. Because nonlinear devices are more prevalent in our electronic designs, especially in power conversion devices, harmonic measurements are very important to understand power quality issues and improve energy efficiency. When you're choosing an instrument, you're going to want to consider published accuracy, which instruments have compliance testing built in. Do they have PLL options to allow you to have integer bins and not have spectral leakage? And do they give you the flexibility to choose specific orders as far as your measurements? Yokogawa develops purpose-built instruments for the measurements of power, including a full suite of power analyzers, power scopes, oscilloscopes, data acquisition products, including voltage and current probes. We have the expertise in making power measurements and have a network of field sales and application engineers to help you with whatever measurement challenges you may face. Please consider making Yokogawa your trusted partner in power. If you have any questions about power measurements and harmonic analysis, we'd be happy to help you. Please find us at tmi.yokogawa.com. Thank you.